All right. Hello, everybody. For me, it's Monday afternoon. I'm a little bit loopy because I've taught 3 classes today, but we're going to give this a whirl. Um, in the Nearpod, I will be sending to you. There'll be a self-paced Nearpod. I'm going to post that to you today, so you have that available. And this needs to be taken care of. This needs to be watched before those Wednesday, Thursday classes this week. So let's get started. We're still working on the standard 2-7 and talk about how there is an interaction amongst the spheres and how they change. Specifically, right now, we're talking about the geosphere portion of 2-7. So, our previous lesson, we did fossils. We talked about petrified fossils. Remember, Medusa turned to stone, carbonized, being the carbon imprint, mold and cast, the yin and the yang. And then we talked about trace fossils, what's left behind, that indirect evidence. And then we talked about the last one there was preserved, wholly preserved, and that's the one that we can get DNA from. So, quick overview of what we did in the last lesson. Let's move forward. Today's lesson is on the geologic timescale. So, Earth has changed. We saw evidence of that. We manipulated that Pangea exercise last time, and we saw how there was rock evidence and how they matched up, and we looked at the fossil evidence and how that matched up. And then what I thought was really cool is at the very end we clicked on that glacier, and if we had the fossil evidence lined up, the glacier evidence was lined up as well. So lots of evidence that Earth has changed over time. Still the same processes. I don't want you to get that confused. Hutton was still correct when he said that the processes that are occurring today on Earth are the same processes that occurred then, 4.6 billion years old. Earth is 4.6 billion years old. Okay. We have a lot of evidence that Earth is very different, especially with the amount of carbon dioxide that was in our atmosphere due to volcanic activity. And so that's going to really drive our conversation. So this is, again, back to the interaction of those spheres, geosphere, but now we're adding in a little bit of the atmosphere as we talk about Earth's history. And we're going to really do that with Unit 4. So this is kind of dipping our toe into those ideas here. First, we haven't gotten to space yet, but I do need to communicate asteroids, what asteroid is, very large space rock. Many scientists believe that in early Earth, meteorites actually brought water here to our planet. So that's actually very common. Another thing that's very common, the most widely accepted reason for the demise of the dinosaurs is a very large asteroid that struck Earth. So we do have many places around our Earth where we have this iridium. Okay, it's uncommon to Earth, can be found here, but geologists think that this is a space rock, that this indicates that there was an asteroid impact in that area. All right, the geologic time scale. I told you guys we were going to get into this today. Hope you're ready. Divides Earth's history into units of time. So this is going to be really cool. Some of you really like science, some of you really like social studies, and this is kind of taking it the history route. We do this with 2 ways, relative dating and radiometric dating. Okay, relative we talked about already. We talked about the law of superposition, how things on the bottom are older, and as we go up, the layers get younger and younger. And we also talked about an index fossil and how that index fossil, the trilobites, the example that I used, if we look at that certain part of that evolution of that trilobite, and we could say, that one existed 400 million years ago. So everything else in that layer then intuitively is also 400 million years or roundabout. Everything above, again, younger, everything below, again, older. Or if we see a more evolved trilobite, then we could say, that one existed 260 million years ago, right before an extinction. So anything else in that layer, again, is going to be relatively around that time frame, older and younger, again, based on the law of superposition, what is above it or what is below it. Radiometric dating is a lot more complicated. That's a lot more scientific and usually results in destroying the rock, always results in destroying the rock or the fossil that we're testing. So with fossils especially, we really try to use that relative dating so we don't destroy those fossils. But radiometric dating, there's 2 types. Again, we're going to hit that hard next week. but we could use carbon-14 or uranium, and that has very different lifespans. Okay, very different amounts of time that we can use those. GTS, there are 4 levels of division here. This is organization. If you're like me, you're type A, this is right up your alley. This is going to make sense. It's going to be easy. Okay. We're going to understand because it is a graph, it is a chart, and we are efficient minded. Maybe those of us on the creative side might have to work a little bit harder on this one. 4 levels of division. Eon, that's the largest expanse of time. That's the largest division of time. And we're going to talk about four or five of those, but really just 2. We're going to kind of narrow that down to 2. Eras. Eons are subdivided into eras. Eras are subdivided into periods. Epochs are subdivisions or subdivided from periods. And so you kind of look at it like this. If I annotate the screen, we got very large division up here, and then era is a little bit smaller division. Period is a little bit smaller than an era, and then the smallest division of time is called an epoch, not an epoch, but an epoch. Okay. These divisions are determined by one of 2 things. There is a geologic change that we need to say, okay, well, we got to end that time frame there, and we need to move on to another time frame. Or talking about specifically the Phanerozoic eon, that's living organisms. So there are large changes, and that's what we're going to focus on mainly, large changes in living organisms. Earth has a story, just like everything else. That's what history is, right? So we have the Precambrian, and we, for our standards, guys, you're not going to have to talk about the Hadean, the Archean, or the Proterozoic eon. You're not going to have to know those. Those are very large expanses of time in which we don't have much information, and that could be, well, there wasn't much going on. That could be that it just things didn't exist during that time, or some scientists theorize because whatever could have existed or did exist at that time had to have undergone the rock cycle at this point and been recycled back into Earth's crust. So lots of debate on that topic. So we're not going to talk about that as much. That's not where our standards leave us, okay, or start us rather. The Precam, that's what we're going to refer to it to, the Precambrian. The Precam is the largest expanse of time. I've got to understand that. We have 4.6 billion years of time that we are assessing. 4 billion is the Precambrian. Only 0.6 is where we have vast evidence of life. Okay, so only that 0.6 mark is where we have evidence of time. 4 billion years, we don't know. We got speculation, we got some evidence, but really the vast majority of our evidence that we have built Earth's history on is the last 0.6 billion years. Seems kind of crazy, right? That 0.6 is called the Phanerozoic eon. Again, that's going to be our focus. And it was marked by sudden increases in the number of fossils, the diversity of fossils, the number of organisms that all of a sudden just explode, come onto the scene about 540 million years ago. Again, about 0.6 billion. Precam, things were simple. I told you guys, I've talked to you in class. We've gone over this a couple of times. I said it in the last lecture. The overarching theme for Unit 2 is simple to complex. Okay? When you get asked a question, okay, what could be older, a worm or a bird? What existed before? A fish or a snake? Okay? If you think in the lines of simple to complex, okay, you're going to be able to say, well, worms would have evolved first, right? Because they're invertebrates. Or a fish evolved first because it was one of the first vertebrates, okay, came before those reptiles, because I think I compared fish and snake there. So life was simple back in this time. Actually, till pretty recently, we didn't have any evidence, or not much evidence, that anything existed. We do now have evidence. We do have fossils that date back as far as 3.1 million years, but they're very few. And we're talking like single-celled bacteria, blue-green algae that existed in the primordial soup of our oceans. But very simple organisms if we have much at all there. Again, that slide, that's a good representation. That was 4 billion years right there. We just talked about it. That's all we got. All right, Phanerozoic. Now, phanero means visible. You know, I love those words and breaking those down because I think it gives you a good, it gives you something to go back to when you see these words on a test. So phanero, it means visible. Zo means life. That could be Z-O-I, could be Z-O-E, either way. Phanero means visible. Zo means life. So Phanerozoic means visible life. Now we have life coming on the scene here in our fossil record. The Phanerozoic eon is subdivided. Okay, again, Phanerozoic is an eon. If we go back, eon, era, period, epoch, it's further subdivided into 3 eras. Okay, eon, era, period, epoch. And these are further subdivided into periods, which are further subdivided into epochs. So we have the Cenozoic. Ceno means recent. We have the Mesozoic, which means middle. And we have the Paleozoic, which means old. If you think about meso sounds like middle, right? Paleo, like paleontologist, okay, means the study of, or paleontologist studies old things, fossils, things like that, rocks too. Geologists can be that way as well. So I'm trying to see from this slide here. So 5, you're not going to have to narrow down, or probably not going to have to answer a question on any test, especially not a state test or something like that, where you have to give these years. But you may want to know the relative time frame: 544, 250 million. Something happened there. Then we have 250 to 65 million, and something happened there. And then we have 65 million to the present. Okay. The Paleozoic era, okay, explosion of life. It's actually coined, that phrase is coined, the Cambrian explosion, because all of a sudden it's just life existed. The atmosphere was perfect and life just flourished, and we can see diversity of those living organisms in the fossil record. Okay, it's split into 7 periods. Again, eras are broken down into periods. And those you're not responsible for being able to regurgitate those. Okay, it's Silurian, Devonian, Cambrian, Permian, Ordovician. There's also, if you're American, there's Mississippian and Pennsylvanian. Europeans call it something different, but you're not responsible for knowing those out of the gate. You do need to know the Cambrian explosion. You have to know that one. So that is the very first period of geologic time, the very first period, because before that, we had the Precambrian. You wonder why it's called Precambrian, everything before the Cambrian period. All life existed in the ocean. We call this the age of the marine life. Started very simple, right? Again, we had that single-celled bacteria and that algae already. Then we start to see in the fossil records, we start to see some invertebrates come on the scene. So no backbone. Think jellyfish. Very simple, right? And then those invertebrates, we see evolution or evolve into what we call vertebrates, which are fish, things that have backbones. And then those further evolved into amphibians. And then actually right at the end of the Paleozoic, we start to see some small reptiles. And I love this picture right here because it really shows you, it's almost like they just walked out of the water, right? Of course, this happened over millions of years. But as food sources became available, the plant life started to develop on continents. Then, of course, organisms like amphibians began moving out of the water and onto land. And you can see the plant life, how the plant life evolved here. So we've got, seaweed, and we start to get more flora in the water. And then and as we get over here, quite towards the end of the Paleozoic, you see coniferous plants moving out onto land. And again, organisms are going to follow, right? Well, animals, creatures, critters, they're going to follow that food. I love the slide. So dramatic. Every era ends in a mass extinction. Remember I said, oh, look, something happened. This is what happened. Every era ends in a mass extinction. We think what happened was carbon dioxide skyrocketed in our atmosphere. I told you we are going to talk about the atmosphere, okay? Skyrocketed in our atmosphere, probably caused by Pangea coming together. That's what they think. That's the most widely accepted theory, is that Pangea, we had this time of crazy plate tectonics, lots of shifts, Pangeas coming together, forming increased volcanic activities, releasing all that carbon dioxide into the atmosphere, which is causing our atmosphere to heat up. Okay, there's less oxygen, and everything really existed in the water, except remember a couple of things that crept out onto land right there at the end. We call this the Permian extinction. And you need to know that word. I said you don't need to know them all. You don't need to know Devonian, Silurian. You don't need to know Ordovician. You don't need to know those. But the Cambrian, the very first, and the Permian, the largest mass extinction in our history that we know of. Okay? Largest mass extinction. You will see different numbers here. Okay? You'll see 90 to 95%. You know, it's still, a lot of it's still speculation. We're still learning and gathering evidence on this. So that 90 to 95% range, all living creatures were wiped out. They went extinct. And that's sad. It's kind of crazy. I wonder what could have existed that we maybe didn't even know about, right? 90% of all living things wiped out because we had less oxygen. The atmosphere became less favorable. The water became less oxygenized. And critters couldn't live. Okay? Every era ends in mass extinction. Every era ends in mass extinction. Next is Meso. Again, Meso means middle. Makes sense. Y'all gonna love this one, right? There are 3 periods in this era: the Triassic, the Jurassic, and the Cretaceous. I bet just in saying those words, you could tell me what existed during this time. This is called the age of the reptiles, or you might see it the age of the dinosaurs, because they were the apex predator at that time. In the Cretaceous, at the end of the Cretaceous, we start to see some small mammals, but the mammals, they really couldn't get an edge, right? They couldn't get an edge, small mammals, because they were being gobbled up by all those big reptiles. So you can see here in this picture, let me get my little, good. We got the age of the reptiles starting to creep in. Oh, there's our little Pangea, the coniferous trees, during that time period, the age of the dinosaurs, and we start to see birds really come on the scene here. Finally, some little bitty small mammals. And plant-wise, I do need to highlight this. Plant-wise, again, simple to complex. We have cones, and then very end we start getting those flowering plants. Okay. But alas, every era ends in a mass extinction. 65%. Again, you'll see different numbers here, but you will see 60 to 65% of all living creatures were wiped out. There's still lots of speculation about this one. The most widely accepted is that an asteroid about 6 miles wide hit in the Yucatan Peninsula. We talked about iridium already. We talked about it in last class too. But iridium is not widely known on Earth. It's not widely natural. Let me say that on Earth. So when we find a huge layer of this, we know something big happened. This was a big event. And so we can speculate beyond that, that if something that large hit, of course, it would send up debris that would darken out our atmosphere. And at that point, you know, plants need that for photosynthesis. They need that for food. And so the plants die off, and then the smaller critters die off. And then, of course, we get up to the larger critters. And this would have been a global incident for something that size, that speed, to hit and send up that kind of debris. So again, 65% mass extinction. And we also start to see, and this is one of the argued points, we also start to see the breakup of Pangea at this time. So they could have been both, right? Contributing factor. We get that increase in volcanic activity again. Carbon dioxide increases. We have this major global warming. So that's widely accepted theory too. However, we do have the evidence of that iridium layer in that area in the Gulf of Mexico. Last but not least, we have the Cenozoic era. That is the most recent. That is the age of the mammals. If you've ever watched Ice Age, you are walking through the first parts of the Cenozoic era there. Um, Again, you don't have to know all the periods here, the Quaternary period, the Tertiary period. You don't have to know all of that. Probably Quaternary is what you want to know, because that's where we are. It's where we exist in geologic time. But age of the mammals, that's super important. Extinction of the dinosaur basically led the way for mammals to become bigger, more complex. There's that word again, more complex, and rule this era. All right. Again, we see at the end of this era, we see human beings come onto the scene, and that's the Holocene epoch. You do need, that's really the only epoch of geologic time you'll probably see on a test, the Holocene epoch. Okay. So that's human history. That's where human history begins. And then we see an interesting change in evolution here. Instead of what we've seen so far is start small, get big, start small, get big, start small, get big, right? And what we see here is we have evolution of the brain. Organisms are now becoming smarter rather than just larger. It's pretty interesting there. Every era ends in a mass extinction. Why do I not have a slide right here? Well, because we haven't been wiped out yet, so the Cenozoic era has not ended. But if it does, and human beings are still around, they need to come back to this geologic time scale and let them know. End of geologic, or end of Cenozoic era. Moving on to the next. I just put Phanerozoic on here, but I want you to get a good picture of this. Eon, era, period, epoch. Say it over. Eon, era, period, epoch. They're broken down, okay, into categories. Good organization here. Phanerozoic, all visible life. Old, middle, new. Again, we got the Cambrian explosion. You need to know that. If you're in the UK, or really the rest of the world, because you know America got to be different, Carboniferous is what they call the Pennsylvanian and the Mississippian. Here it's kind of like, we're just going to give it something we know. And then the Permian, you need to know that, the largest mass extinction in geologic time. Triassic, Jurassic, Cretaceous, the reign of the dinosaurs. Start to see mammals here, but then we have a large mass extinction, 65%. We think it was an asteroid. And then we have these periods during the Cenozoic, and again, we're in the Quaternary, and the Holocene epoch. So go impress your parents. Say, hey, guess where we are in geologic time? We are in the Phanerozoic eon, the Cenozoic era, the Quaternary period, and the Holocene epoch. I'm sure they'll be impressed. All right, guys, that's all I have for you today, and I will see you in class.